Hello, and welcome to your CNET124 Week 4 lecture video. This week we're going to be looking at the physical layer and numbering systems. There are two lectures. And just for reference, we talked about the OSI model last week and the TCP/IP model. Now these are going to be very, very important, as I mentioned last week. At least I think I did. Very important this semester. You're going to be working your way up the OSI layers, and we're going to start at the physical layer, which is layer 1. The application layer is layer 7. So that's just kind of how we're gonna roll. We're gonna slowly work our way up, and by the end of the semester, you'll know how everything works at all 7 layers, and that's a very important thing for moving forward in the stream of courses that you're in. You need to know the OSI model and the TCP/IP model and protocols that operate at each layer and how they are similar, so you can compare and use them. But generally, we talk about things using the OSI model. Anyway, with that, let's move on to the physical layer. Now, the physical layer, of course, is layer 1. By the end of this chapter, you're going to be able to talk about its purpose, its characteristics, different types of cabling we use, and when they're used, and why they're used, and disadvantages and advantages to each. And when we're talking about cabling, I'm including wireless in there as well. With wireless, there are, of course, no cables, right? But the underlying technologies, the underlying logic, all works more or less the same. It's just the connection end of it works a bit different, if that makes any sense. So, at the physical layer, you need a physical connection, right? Before you can send data over the network, you have to be physically connected to the network. That makes sense. Now, this could be a wired connection. It could be a wireless connection. It depends on what type of network you're configuring. And this applies to any network, whether it's a corporate office, whether it's a home, whether it's anything in between. Everything's physically connected at some point, and even wireless counts as a physical connection. Now, to connect to a network and send traffic over the network, a device has to have a NIC, a network interface card. And even your smartphones and tablets, if you have a tablet, they do have a NIC built into the board on the inside. It's on board and it's very tiny, but there's one there. Well, there's actually more than one, right? Some devices have one NIC, others have more than one. You can have more than one. So if you've got wired and wireless, for example, you have more than one NIC. Going back to my smartphone example, you've got multiple NICs in there because you can connect to your 4G and 5G provider network. You can connect to wireless. This requires multiple NICs, right? Now, not all physical connections offer the same level of performance, as you're going to learn. In fact, and I'm probably going to mention this later because I'm going to forget I mentioned this, but I want to mention it now. You're always going to get a faster, more stable, better connection out of a hardwired, physical wired connection over wireless. So the physical layer is responsible for transporting bits over the network media, and it completes. It accepts a frame from the data link layer, layer 2, and it encodes it in some representation of binary. It's not actually sending like binary ones and zeros, right? It's sending some representation of binary that the device at the other end can reinterpret and put back together. It's the very last step in encapsulation, which we talked about encapsulation and decapsulation previously, right? And the next device in that path between source and destination will receive the bits and re-encapsulate the frame and then decide where it goes and what to do with it. That makes sense so far. So the physical layer, we're talking at layer 1, right? Down here. everything we use at the physical layer, and some stuff at the data link layer too, are hardware implemented things, and they're governed by organizations such as the ISO, EIA, TIA, the ITU, ANSI, and IEEE, which we're going to talk about later. In fact, we already previously talked about the IEEE. I think, if I remember correctly anyway. So the physical layer is any standard that works at the physical layer has to address three functions. It has to address how the physical components are used and how they work, how data is encoded, and signaling, which we're going to look at in a minute. Now, physical components are the actual hardware network devices themselves, the media, and any connectors that are used to connect those things. So things like hardware NICs, interfaces, connectors, cables, different types of cables, different cable designs, all have associated standards at the physical layer. We're going to look at some of them today. You may be wondering what encoding and signaling are, and we're going to look at those now. Encoding is converting the stream of bits into a format that's recognizable by the next device. The coding provides a predictable pattern that can be recognized, and this is agreed upon when the connection is made. Some examples of encoding are Manchester, 4B, 5B, 8B, 10B, NRZ, non-return to zero, and NRZI, non-return to zero inverted, which aren't on the slide, but I like to mention because like NRZ sounds cool. Signaling is how the bit values 1 and 0 are represented on the medium. So the method of signaling varies based on what type of medium you're using. So for example, if you're using fiber optic, you're using pulses of light. If you're using wireless, you're using microwave signals. If you're using copper cables, then you're using voltages. You've got peaks and valleys, right? One can represent one state, the other can represent the other state, 1 and 0. That's the great thing about binary, is that anything that can be used with two states can be used to represent binary. When we're dealing with data and sending our connections and sending data out over a connection, we're usually talking about bandwidth. Bandwidth is the capacity at which a medium can carry the data. Digital bandwidth measures the amount of data that can flow from one place to another over a time. So how many bits per second? Physical media properties, technologies, and laws of physics all play a role in determining what the possible bandwidth is. We tend to use various units that you should be a bit familiar with by now, but maybe not. Should have at least heard in this day and age. Things like probably not bits per second or kilobits per second, but megabits and gigabits per second you've probably heard quite a bit, at least if you've signed up with an ISP or something like that, right? You usually talk about your connection speed in those terms. And terabits per second, you usually don't see that much unless you're dealing with corporate grade infrastructure where you require very, very fast connections. When we're looking at bandwidth, we actually look at a couple different terms. We look at latency, so that's the amount of time that it takes, including delays from data to travel from one point to another. And we look at throughput and goodput. Throughput is a measurement of the total amount of data that could pass over the media over a time period. Now, that data that's passing over that media in the throughput includes a lot of things like control data, which isn't part of your real data, right? Like frames, for example, aren't part of the actual data that you're sending. They're additional overhead that's required for networking to happen, which is why if you're with an ISP like Rogers or Bell that charge you for your monthly usage or have monthly usage caps, they're ripping you off because that's how they do it, right? There's all that overhead that counts towards your usage. usually anyway. Good put is the measure of usable data over the time period. So all of that data, all of that throughput, minus the overhead, minus the frames and packets, frame headers and packet headers and footers, right? The actual data. So good put and throughput. Hopefully that made sense. So we're going to look at a couple different types of cabling. First up is copper. Copper cabling is one of the most common types used in networks today. You're going to find it everywhere. And that's been the case for a very long time. And there's reasons for this. It's cheap, it's pretty easy to install, and it has a very low resistance to electrical current flow, so it's good for networking. It has some limitations though. Copper cabling has an attenuation length associated with it, which we're going to look at in a bit. So the longer the cables get, the weaker they get, the longer the signal gets, the weaker it gets. And they're also susceptible to interference from two sources, which can corrupt the data, it can distort it, and it can cause issues with your packets and make you have to resend data because it arrives at the other end in a corrupt format. These are EMI, electromagnetic interference, RFI, radio frequency interference, and crosstalk, which is the two wires, because they're next to each other, could interfere with the functionality of the other. Data passing on the one could not explaining this good, I feel, could have a side effect to something on the other wire. To mitigate against these, you just adhere to the cable length limits. And when you've hit that limit, you need to put in another router or a repeater or something, another piece of networking equipment, before you can continue that cable run. To mitigate against EMI and RFI, there's types of copper cabling you can buy that are a little bit more expensive that will mitigate against these by using metallic shielding and grounding. And with crosstalk, to mitigate against that, you actually just twist the wires together, and that mitigates against that completely. And in fact, when you look at the inside of a cable, as we're going to see in a minute, it's made up of 8 wires that are twisted into groupings of 2, so you get 4 groupings of 2, making your 8 wires. They're usually called a twisted pair. That's where we get the name for the cable. So with copper cabling, the most common types you tend to see are unshielded twisted pair, or UTP, shielded twisted pair, or STP, and coax. Unshielded twisted pair is by far the most common because it's the cheapest. These are terminated with RJ45 connectors. You've seen these. You've been using them in the labs. We're using unshielded twisted pair with RJ45 connectors. So those little clippy things on the end, that's an RJ45 connector. These are used to interconnect hosts with intermediary networking devices. And you can even use them to interconnect intermediary devices, so routers and switches, as we've seen. They do have an outer jacket, a plastic outer jacket, that protects the wires from damage, and the cables are twisted in pairs to protect from signal interference. They're color coded, so you can figure out which one is which one on the other end of a run of cable. And that color coded insulation is more than just to tell you what cable is what. It's actually plastic insulation to isolate the wires from each other as well, to give it some shielding against, to mitigate against RFI and things like that, crosstalk. Now, shielded twisted pair is a bit more expensive, and it's a bit harder to install. It has much better noise protection against EMI and RFI. It's still terminated with RJ45 connectors, and you'd use it for the exact same things that you would use unshielded twisted pair. If you've got a lot of a lot of EMI and RFI in an environment, you might want to invest in these instead. They've got a few extra things within the cable. They've still got an outer jacket that protects the copper wire from physical damage, and they still have the 8 wires that are twisted in pairs internally with the color-coded plastic insulation. But they also have a braided or foil shield to protect against add some protection to against EMI and RFI. And they have a foil shield for each pair of wires as well to further isolate them from each other. So it's pretty great. It's a bit more expensive, but if you've got a lot of sources for EMI and RFI and your network performance is really bad, maybe upgrade to some of these and then it's worth it. Another one you tend to see is coax. If you're with Rogers or any Rogers reseller like TechSavvy, you've got cable internet at home, you've seen coax cables, right? They've got an outer jacket, just like our shielded and unshielded twisted pair. And then they've got a woven copper braid or metallic foil, kind of like the shielded twisted pair cable. Then there's some plastic insulation that insulates and protects the copper conductor. There's a single wire that's used to transmit the signal. And there's there's many different types of connectors, but there's 3 shown on the slide there. They're commonly found with cable internet providers for the on-premises wire coming out of the wall going into your modem. It's usually a coax cable. You might also see it in wireless if you've got large antennas. I'm talking like industrial grade wireless, right? Not your wireless router at home. You might use a copper connector, or a coax cable to connect that antenna to your networking equipment. Sorry, I thought I paused there. You heard me drinking. Oops. Try to pause in the future. I usually do. I thought I'd hit it, and I did not. So unshielded twisted pair. 4 pairs of color-coded wires twisted together. There's no shielding. It relies on cancellation to limit crosstalk, and one other thing that we're going to look at. So each wire in a pair uses the opposite polarity. One's positive, one's negative. And they're twisted together so the magnetic fields cancel each other out. Or at least to cancel the outside EMI and RFI. There's also variations in the number of twists per foot for each wire. Each wire is twisted a slightly different amount, and that helps mitigate against crosstalk in the wires within the cable. It's a good thing. When we're wiring them up, there's a couple different standards that we use, like the TIA or EIA standards. And these define things like your cable types, your lengths, your connectors, how you terminate them, and different methods for testing them. If you've ever bought what non-networking or non-educated networking folk tend to call just a network cable, an Ethernet cable, or a twisted pair cable is more appropriately the term, right? It's not just an Ethernet cable. Everything uses Ethernet. You've probably picked one up off the shelf and it said it's a Cat 5 or a Cat 3 or a Cat 5e or a Cat 6 or something. What? That's actually short for and means something. It's a category. Category 3, Category 5, 5e, Category 6, and so on. These are the IEEE's standards for rating the performance of the cable. Which makes sense. So the higher the number, the better the performance, the more it's going to be able to send through it. So these are usually terminated with RJ45 connectors, which look like this, and you've seen them in the lab. They connect into an RJ45 socket, and that's what they look like. And if they're properly terminated, we used to actually make them in this course. You should see the connector come down over that outer jacket and be crimped. If they're poorly terminated like this, and you see some exposed wires here, there's definitely going to be some data loss, and the performance on this cable is going to be a little bit worse. It might still work. It might not even work, right? If these cables don't actually hit the end of the connector there, then it won't work. They have to be touching that connector for it to work. But if it does work, it's not going to work as well as one that's properly terminated. Now, there's a couple different ways you can wire these up. There's two different standards, T568A and T568B, and there's the color coding for the wires. You tend to see straight through and crossover, at least you used to. You don't see crossover anymore, and rollover are the three different types of wiring. We've been using rollover, and we've been using straight through cables too. With the straight through cable, both ends are connected the same way. So they're either both connected, are both wired to T568A or T568B, and they're used to connect hosts to networking equipment, and you can use it to connect switches to switches and routers to routers as well. Technically, you're supposed to use a straight through cable when you're connecting two devices of different types, like a switch and a router. And a crossover cable when you're connecting two devices of the same type. We don't do that anymore. They're legacy, because most NICs now use auto MDIX. So they'll sense the cable type and complete the connection regardless of which type of cable you use. So it doesn't matter, we just use straight through across the board. With crossover, one end is wired to one standard and the other end is wired to the other standard. And the other one you've seen already is the rollover cable. It's a Cisco proprietary cable. We've seen them in the labs. We've been using them, right? They're the thin light blue cables that you see coming out of the back of your computer going into the port on the wall. And those connect a serial port on a host to a router or switch's console port so you can configure it. They're used for configuration only. Whenever we're sending data, we're sending it over a straight through cable. And data includes things like ping and traceroute, any other communication. Hopefully that makes sense. Normally I'd pause and ask if that makes sense, but no time to pause. Now fiber is a totally different type of cabling, fiber optic cabling. It's not as common as UTP because it's expensive. It's really expensive. It's great for some networking scenarios though, so it's worth the expense if you got the money. You can run fiber over much longer distances and at much higher bandwidths than any other networking media. That's why it's great. It's less susceptible to attenuation because of the much longer distances, right? It's completely immune to EMI and RFI as well. And it's actually made of flexible, extremely thin strands of glass. Very, very pure glass. And data, when you send data over a fiber optic cable, is sent using either a laser or an LED, which encodes the bits as pulses of light. Light moves faster than anything else. That's why fiber optic is faster. The cable itself acts as a waveguide to transmit the light between the two ends with minimal loss. There's a couple different types of fiber, single and multi-mode. Single mode fiber has a very small core. It uses very, very expensive lasers, and it's good for long distance application. Multi-mode fiber has a larger core, uses less expensive LEDs, and they transmit the data at different angles so you can interweave different paths of light on the same connection at the same time. And it gives you up to 10 gigabits per second over 550 meters. Dispersion refers to the spreading out of light over time. And the increased dispersion means increased loss in the signal strength. Multimode fiber has greater dispersion than single mode fiber. That's why your maximum cable length is 550 meters, because at that point it starts to, the signal, well, just becomes unusable. Fiber is commonly used in enterprise networks for your backbone cabling or your core infrastructure. Some organizations or ISPs like Rogers offer fiber to the home, so it's always on broadband, and it's much faster than cable and anything else you get. It's used in long haul networks to connect countries and cities by service providers, and the internet actually uses fiber optic cabling. The internet actually has all of the continents in the world are connected with fiber optic cables that run along the ocean floor, interconnecting the different continents. That's how the internet works. They're submarine cable networks. So, it's pretty cool. Anything we do with fiber in this course, we're going to be looking at fiber within the enterprise only and not the others. But it's good to know the others exist, and we're not actually going to do much with fiber other than maybe look at some fiber providers in one of the labs later. Now fiber, unlike our twisted pair and shielded twisted pair, which use the same type of connectors, fiber has a couple different types of connectors. There's straight tip connectors like these here. Lucent connectors, duplex multimode lucent connectors, and subscriber connectors. So you might see, depending on what you're connecting, you may see these. Also, you might not be dealing with connecting them because, well, there's hazards for connecting them, as we'll see. These are the different types of patch cords you can see. Usually you see either yellow, orange, or aqua jackets. Yellow for single mode, and orange or aqua for multi-mode fiber. Just so it makes it easy to see what it is you've got based on the color of the cable. So it's primarily used for backbone cabling for high traffic and point-to-point connections. For connecting buildings and multi-building campuses. And here's a comparison here on the benefits of unshielded twisted pair and fiber. So unshielded twisted pair, you'll get a bandwidth of 10 megabits per second up to a maximum of 10 gigabits per second, and you're never going to see that maximum, right? There's additional overhead and other reasons that you're never going to see that maximum. Fiber supports 10 megabits per second up to 100 gigabits per second, so much faster. The attenuation length for unshielded twisted pair is 100 meters. So every 100 meters you need to have a repeater or another piece of networking equipment connected, such as a router or a switch, depending on how you're configuring these, to rebuild the signal, or it's just not going to work. Fiber, the attenuation length is 100,000 meters, so it's much longer cable runs we're dealing with. Unshielded twisted pair does have some immunity to EMI and RFI, but it's very low, and some immunity to electrical hazards, but again, it's very low. Fiber is completely immune to both of these things. We don't even have to worry about it, because they're pulses of light we're dealing with. Unshielded twisted pair, the media and the connectors are cheap, it's easy to install, and you don't really need any safety precautions for like dangers coming from actually touching the equipment when you're installing it. Fiber, on the other hand, is very expensive, both the media and the connector. It requires a lot more skill to install, and you have to have higher safety precautions because there are significant hazards when you're installing this. Hopefully that makes sense so far. Normally I'd pause and ask for questions, but We're just going to keep going because this is a video. We're going to talk about wireless now. Everything you do with a wired connection, we just looked at different wired connections, you can do with a wireless connection. It just works a little bit different. So it uses either radio or microwave frequencies to carry signals, electromagnetic signals that represent binary ones and zeros. It's great if you need mobility, because you can move around everywhere, right? You can imagine dragging an Ethernet cable around the office. Wouldn't be great. And it's become very popular, and it's like over the last 15 years. It's gone from like nobody had it to everybody uses it. Or I won't say nobody had it, but fewer people used it, right? Now everybody uses it. There's some limitations though, right? The coverage area can be impacted by your physical location, the characteristics. You get things like walls, right? Radio and microwave frequencies, while they can penetrate walls, they're going to get a lot weaker. And certain types of wall materials, like concrete, they can't really penetrate very well at all. They're susceptible to high levels of interference, and they can be disrupted by other common devices, like microwaves. I used to lab assist at Seneca for a wireless course, and we had one student one semester who was having issues with his router every time he used his microwave. He got kicked off the internet, or kicked off the network. And the professor suggested, well, sounds like your microwave might be going. It's an older microwave. And he said, yeah, it's like 15 years old. He said, yeah, you might want to go replace it. Sure enough, he went out and replaced it. And no problem. Fixed it. Alternatively, he could have just set his network to another frequency, which he ended up doing before he went out and replaced it. And that fixed the problem too. But, I mean, if a microwave is interfering with your wireless, it's probably leaking something that you don't want it to be leaking, so best to replace it. Wireless is difficult to secure because everybody can access it. There's no required physical media that you have to connect to, right? You can see the transmission. So there's lots of security concerns with wireless, and it's a shared medium. So unlike wired, which operates in full duplex, generally speaking, wireless only uses half duplex, which means one device can send or receive at a time. And the more users you have in a wireless network, the lower your bandwidth is going to be. We have various IEEE and telecommunications standards for wireless that cover everything from the physical link and the physical layer and the data link layers. But in each of these standards, the physical layer specifications dictate your data to radio signal encoding methods, your frequency and power of the transmission, signal reception and decoding requirements, and the design for your and construction for your antennas. You're going to see when you're picking up networking equipment and Wi-Fi, if it's Wi-Fi routers and switches you're picking up, or routers and NICs is what I meant to say. You're going to see 802.11, which is an IEEE standard. And in fact, if you've picked up a router, you've seen it's 802.11 AC or AX or N or something. That's the revision to that standard, AX being the most recent. Bluetooth, that's 802.15, which is wireless personal area networks. WiMAX is 802.16, and that's a point-to-multipoint topology for wireless broadband. And Zigbee, which is 802.15.4, so it's an extension to Bluetooth. It's a low data rate, low power consumption wireless connection. It's used for IoT applications. Anytime you see 802 dot something, you know you're dealing with an IEEE standard, because that's the way they are. Wireless LANs consist of access points and wireless NICs. You have to have a wireless access point. At this point, I'd point to the ceiling in the classroom. If in the classroom, you tend to see usually there's 2 in every room. They're little white boxes that you've probably not noticed. They're actually wireless access points. So these concentrate your signals from your users, and they are connected to some back-end controller through probably a copper connection, unshielded or shielded twisted pair. And then you've got wireless NICs, which actually provide your communications capability to your hosts. And everybody's used these, right? There's a bunch of different wireless LAN standards, and when you buy networking equipment, make sure that everything works. Conveniently, new equipment is always backwards compatible, so that's great. Whenever you're deploying wireless within a network, though, you have to think about security, you have to think about access, and ways to protect those from unauthorized access and damage. So you tend to, we're going to look at VLANs later, much later, I think next semester. You tend to segregate wireless traffic to its own virtual LAN, so you can apply security policies and whatnot to that specifically. And that brings us to the end of our first of 2 sets of slides today. So I'm going to pause, get that set up, and we'll continue. So Chapter 5, Numbering Systems. We're going to look at a couple. We're going to look at binary, because computers work in binary. We're going to look at hexadecimal, because it's important to be able to represent things in hexadecimal as well. We tend to use hexadecimal for things like IPv6 because the numbers are much bigger, there's a larger number of bits. Hexadecimal is used to represent binary. And we're going to be able to, by the end of this, I'm going to teach you how to convert numbers between one and the other, right? From binary to decimal and back again, and from decimal to hexadecimal. We're actually going to go to binary as a stepping stone or an intermediary, and do it that way, because it's one of the easiest way to do it. So binary. Binary consists of ones and zeros, right? 2 states, hence binary. These are referred to as bits. Now, decimal numbering system consist of digits 0 to 9. We've used these all our life, likely. Can't think of anybody who wouldn't have used these all their life, but I'm sure everybody has. We tend to see IPv4 addresses and IPv6 as well, but we're going to talk about IPv4 specifically. Every device needs an IP address to identify itself uniquely on the network and to be able to communicate. So hosts, servers, network equipment all use binary to identify each other, binary addressing. Now, when we look at an IP address, it's not binary. It's a dotted decimal notation. It's 32 binary bits divided into 4 sections called an octet. And each octet contains 8 bits. It's separated by a dot. So we tend to use that dotted decimal notation, right? Each octet can only have values between 0 and 255 as well, because there's only 8 bits. So we see them like this, right? But computers and networking equipment see IP addresses in binary. So it's important to be able to convert between them. Now, how do you do that? Well, we're going to look at the slides very briefly, and then we're probably going to deviate from that, and I'll show you a better way. In fact, I'm just going to show you a better way, because this is overly complex and confusing. So to convert from binary to decimal, you need to know your powers of 2. I've already got them written out, but I'm going to show you a couple easy ones. Let's make that a bit bigger. Why is that? Oh, because 10 should be down here for it to align properly. I think. I don't know. Something's funny there. Anyway, With binary, you need to know your powers of 2 because it's a base 2 numbering system, right? So 2 to the power of 0 is 1, of course, because anything to the power of 0 is 1. 2 to the power of 1 is 2, because anything to the power of 1 is itself. And then we just keep doubling as we go up, right? 2 to the power of 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. Let's make that a little bit bigger. Maybe you can read that now. And so on and so on. Well, you could memorize these as infinitely as far as you want, at least up to 2 to the power of 20. I found it useful to memorize a couple benchmarks and then work your way up and down. So 2 to the power of 10 is 1024. It's easy to remember. If you know that, you know 2 to the power of 9 is half that, which is 512, and 2 to the 11 is twice that, 2048, which is a fun game to play on your phone if you're stuck on the subway and you don't want to play the dinosaur game in Google and Chrome. Now 2 to the 20 is actually a really cool 2 to the power of 20. There's a really cool trick for that that a professor showed me once, and I've never forgotten. It's 10, 4, skip 1, 5, skip 1, 6, backfill 7, and 8. It's 1,048,576. Now that I've shown you that, you're probably never going to forget that. I haven't forgotten that. I was showing that once, 11 years ago, or something like that. Probably closer to 12 now. So you know if 2 to the 20 is that, then 2 to the 19 is going to be half that, and 2 to the 21 is going to be twice that, and so on and so forth. So how do we do a decimal to binary conversion? First we'll go that way, and then we'll go the other way. With decimal, when you've got a decimal number and you're going to binary. I'm just going to pick an arbitrary number. I'm going to go 467. Why not? I just kind of typed it on the keyboard. There's other ways to do this. You can use algorithms and formulas and stuff, or you can just do some simple subtraction. You take the highest number of 2, the highest bit value that you can subtract out without going under, and you subtract that out. So this is going to be minus 256, right? Which is going to give us 210. Right? 210? I think that's right. Nope, 220. I'm actually going to double check that quick. I was right. It was 220. Had I gone with that initial assumption of 210, I would have made a mistake that I would have come to regret later. So next, whoops, we got a bunch of ones we don't need. I'm going to space that over once just so our signs line up properly. We're going to subtract out the next highest bit value. We're going to just keep going down and subtract down until we got nothing. So that's going to be 128, right? And that's going to give us, drum roll please, I'm totally putting it into a calculator because it's late and I'm tired. I'm going to make dumb mistakes if I don't. It's going to give us 92. So we can subtract out 64, right? So that's going to give us 28. We can subtract out 16. That's going to give us 12. That's right, yeah, 12. We can subtract out 8. It's going to be our next one. We're going to get 4. Right? And we can subtract out 4 from 4. So we just kind of keep going down, right? And we get 0. Now, for the binary representation of this number, I'm going to do it on this line here. We just simply go through our list, and starting from the biggest value we subtracted out, anything before that is a 0, we don't need to represent it. Unless we're trying to represent that as something, say, like an octet, right, where you need the full 8 bits. But if you don't, and then you just pad it with zeros in the front. If you don't require that, however, you start with the highest bit value you subtracted out and work your way down. Anywhere you subtracted, you put a 1. Anywhere you didn't, you put a 0. So we subtracted out 256, we subtracted out 128 and 64, but we did not subtract out 32, so we put a, whoops, not a 3, a 0. 128, 64, 32. Sorry, 256, 128, 64. We didn't subtract 32. We subtracted 16 and 8 and 4, but not 2 or 1. The trailing zeros matter. We need those, so we know where the ones sit, right? They're placeholders. But the leading zeros are assumed. This is 0 infinitely in front of it. So decimal, we get, or 476 in decimal, we get 1110, 11100. Make sense? Let's do another one. I'm just going to keep that around because we can take that and go to hexadecimal after. So let's do something a bit bigger, a bit smaller. Let's do 230. Why not? Let's make that. That's probably good enough. So same thing. We subtract out 128. We're gonna get, whoops, 102. I think I did that right. I'll double check that again because it's late and I'm tired and I'm prone to making stupid mistakes. Hey, I did that right. Nice. So next we subtract out 64, right? That's the next bit value we can subtract out. We get 38. This one's going to be easy. So we're going to subtract 32, of course. We're going to get 6. Oops. We're going to subtract out 4. Whoops. I do actually prefer doing this on a whiteboard. We're going to get 2. And we're going to subtract out 2 and get our 0, right? It's tedious doing it this way. If you ever make it down here and you've got something that's not 0, that doesn't subtract evenly and give you 0, you know you made a mistake somewhere. Go back and fix it. So 230 in binary is going to be, we subtracted 128, so we put a 1. We subtracted 64, so we put a 1. We subtracted 32, we put a 1. We did not subtract 16 or 8, but we did subtract 4 and 2, but not 1. So it's going to be 1, 1, 1, 0, 0, 1, 1, 0. Okay, so far? Hopefully. Hopefully that makes sense. Now back to our slides. So here's what an IP address would look like, right? We break that down into binary bits. Again, because we want to keep these padded to 8 bits, we're going to include those leading zeros that I said were assumed. So when we put the number together, it makes sense. Now hexadecimal is useful for a variety of other things, for representing larger binary numbers in a simpler way. They're useful for IPv6, and when you to understand what you're looking at and to subnet, you're going to have to be able to convert these hexadecimal numbers to decimal and vice versa. Hexadecimal is a bit weird. It's a base 16 numbering system, so it uses numbers digits, numbers, same thing, 0 through 9. And then when we get to 10, we do something funny. We start counting with letters. A, which is 10, B, 11 becomes B, 12 becomes C, and so on and so forth, all the way up to 15, which is represented as an F. This way you can express a value a single value that represents four binary bits. Each hexadecimal number is 4 bits. So they're useful for a lot of things. They're used in IPv6 addresses, they're used in MAC addresses, they're used in other places in computing too, like hex color codes if you get into anything to do with web design and color. IPv6 addresses are 128 bits in length. And each hextet, each grouping, is 4 bits. Well, let's get it. We're not in the groupings yet. Every 4 bits is represented by a single hex digit. So we've got a total of 32 hexadecimal values that make up an IPv6 address, or 128 bits. There's a lot more IPv6 addresses because of this, as we're going to learn later. Each of these groupings is separated by a colon and is referred to as a hextet. Again, I'm going to divert from the slides because I cover this in a different way. And that's going to be the end of it. So remember those two numbers we converted? We took 476 and converted it to binary. We took 230 and we converted it to binary. That's going to be your first step. If you're ever going from decimal to binary, is to go, or decimal to hexadecimal, or vice versa, go to binary first. I guess I could have showed you binary from binary to decimal. We'll do that in a minute. So we've got our binary number. We want to make this a hexadecimal number, right? So we split our number into groupings of 4. We're going to pad our zeros. So we've got each of these is going to represent a single hex value. This is going to be 1. Whoops, hit a number there. Or a letter. I hit something weird. This is going to be 1 plus 4 plus 8, that's 12, 13, which is going to become D, right? This can be upper or lowercase too. It doesn't matter. And this one's going to be 12, right? 8 plus 4 is 12, which is going to be C. Whoops. So that becomes, we're going to take our extra spaces out now just to make it readable. Whoops. I think I messed up my number. Maybe I didn't. I don't know what I did. That becomes 1DC. Now when you're writing out hexadecimal numbers, it's preferable to put a 0x in front of it, just so you know it's hexadecimal. Because you could have, for example, 456. One of those two is hexadecimal. How do you know? Well, I put 0x in front of it, right? They're different. Could even be the same number, right? This could be 0x456, which is totally different than 456 in binary. Or in binary and decimal. So just stick the 0x in front. Let's do it again. We've got our decimal value. We split it into our groups of 4. That becomes 8 plus 4 is 12. Plus 2 is 14, so that's going to be E. Oops, not R. And this is going to be 1, 2, 4. This is going to be 6. So this is going to be E6. Again, we collapse that back down. We put a 0x in front. And this could be upper or lowercase, right? So that's great. You've seen 2 examples of decimal to binary. And binary to hexadecimal. Well, how do you do binary to decimal? If you're going the other way, you need to know how to do that. So let's give you a binary number. I'm just going to make something up with a bunch of 1s and 0s. It's literally just the reverse of what we just did. Instead of subtracting, you're going to add, right? Remembering our powers of 2 here. So this is going to be 1. I usually start left to right and work my way up because it's just easier. 2 4, 8, 16, 32, 64, 128, 256, right? And we align those properly, and then add them up. Let's make sure I didn't fuck it up before we start in. So 256, 1, 2, 4, 8, 16, 32, 64, 128, 256. Right. So we just add them up now. So we get 10, 16, 17, 18, 19, right? I could have used my calculator and cheated, but I'm not going to. We carry the 1. We get 6 plus 6 is 12, 13. 3 down, carry the 1. We get a 3. So it's 339. Make sense? Now how do you get good at these? Practice. One more. This one's going to be maybe a big one. I don't know. I don't know how many numbers I hit there. We'll see. We're going to go through the same process. And I'm actually going to leave a placeholder for my carry. So that's 1, 2, we have 4, right? 8, 16, 32, 64, 1, 2, 4, 8, 16, 32. Oh, we don't have 64. 128, 256, and 512 are our last two. I'm going to space them out properly because I'm doing this on the keyboard. And then, again, just add them up. Just add them up. So we get 10, 28, right? Taking a few shortcuts there, as I tend to do. We're going to carry our 2. And I'd probably want to check this with a calculator normally. So 5, 8, 10, 11, 12. 2 down, carry the 1 again. And that's going to give us 8, right? So that's 828. There you go. 2 examples. Now you might be thinking, sir, you showed us how to do binary to decimal and binary to hexadecimal. Well, what about hexadecimal to decimal? Well, you just use binary as an intermediary. And I'm going to do 2 hexadecimal to 2 binary for you. So let's make up a number first. F3, 6. I'm going to put a 0x in front, right? Because that's good practice. And 0x, 4E, A, 2. I don't know, something bigger. First one here. We know each of these represents 4 binary digits, right? F is going to be 15, so that's 1111. 3 is going to be 0, 0, 2 plus 1, right? I'm putting some spaces in there, and then we can concatenate it. We can join it together. Now 6 is going to be 0, right? 4 plus 2 gives you 6. There we go. Now we just combine it up. And there's F36, our hexadecimal number in binary, which we could then convert to decimal if we chose to do so, right? Which is going to be a big number. I'm not going to do it because it's going to be a big number. Same thing. So we got 4 EA2. So 4 is going to be 4, right? E is going to be 14, which is 8, plus 4, which gives us 12, plus 2. A is going to be 10, which is 8 plus 2. And 2 is going to be that there, right? So we concatenate those again, and we get our decimal value. And then if you wanted to take that and make it, we get our binary value. If we wanted to take that and make that a decimal value, you would just do the math and add them up. This is going to be a useful thing. I can go over some more practice in the lab this week if you desire more practice. On that note, take care, be safe, thank you for watching, have a great week, and I will see you in this week's lab. And we'll do some of this in the lab, but we can go over some more practice if you need it. Have a great day. Bye for now.